keep in mind when we talk about the atmosphere and when we deal with what's going on and we start talking about climate change and greenhouse gases and in general pollution, it's based on chemical reactions. So we're going to do a quick review of chemical reactions. Now, a couple of points from from what we just finished. Bonding, you either have ionic or covalent bonds. So remember, with ionic, we have that exchange of the electron. With covalent, they share. And so when you have a covalent bond, there's shared electrons. When we have ionic, it's an exchange. Electrostatic, we see specific properties associated with them. But the point here that you want to pick up on is that the ability to form bonds, oops, let's make that in green, okay? The ability to form bonds, okay, the capacity to react depends on the nature of the atom. Now, why that matters is because when we talk chemical reactions, we have a process where we see chemical changes. Keep in mind, chemical changes were color change, production of precipitate, production of a gas. We see something new that wasn't there before. That means that when you look at things, we have to get something new. It's going to have completely new and different properties from what it was original. And we always have what was present before, the reactants, and what was present after, the products. Now the point here is I want you to recognize that this is our chlorine gas. Okay, notice green, poisonous, used in World War I to kill soldiers. We have sodium metal. Look how soft it is. Okay, easily sliced with a knife. And then we have the products, sodium chloride, table salt, which we eat all the time. So these two things will kill us. This we have to have to live. So again, it goes back to that difference in, okay, new, we get new, completely new properties, new physical and chemical, and before versus after. Okay, that's real important when we talk chemical reactions. Now, when we talk chemical reactions, we know a couple of things. First, matter can't be created or destroyed. Now this means that mass before a reaction has to equal the mass after the reaction. You saw this with the baby bottle lab. Okay, when we did the baby, I mean not the baby bottle lab, just the little, we had our water bottle, right? Oops, that's a terrible bottle. In any case, guys, here's my little pipette. Oh wow, that is really bad, huh? And here's my vinegar. So this was my vinegar. Here was my pipette with baking soda. And you masked everything before, and then you masked it after you shook it. Okay? So you shook it, and then you had the mass after. And the significance about the lab is that we noticed that the lab showed that matter was created, that matter was not created or destroyed. In other words, the mass that I started with, here I have 12 grams plus 32 grams equaling 44 grams. In other words, my yield is my equals sign. I have my reactants and my products. I can't create or destroy matter. So another example, if we look at this, if I have calcium chloride and sodium sulfate, I mix those, I get a precipitate and a solution. My mass before, my mass after is the same, but I'm not always given the masses. So that's where chemical equations come in. Chemical equations, CaCl2, Na2SO4, okay, our formulas, producing our products. Now, the point here is, notice when I look at this particular representation, here we see mass isn't created or destroyed, but when I look at it in terms of the atom scale, matter seems to be created or destroyed. In other words, look, I have two Cl's and I have two Na's, but I only have one of each over here. I seem to destroy matter. So that's why we balance them. Okay, and this is where Mino comes in and becomes so important. Okay, Mino. Metals, ions, nonmetals, oxygen, hydrogen. Keep in mind, just like we talked about, if an element's in multiple compounds on the same side of the reaction, we do it last. Okay, so metals, what are my metals? Well, my metals are the calcium and the sodium. I have 1 to 1, I'm good. Sodium, I have 2 here. I only have 1 here, so I'm going to balance that. Now, when we look at the next thing, the ions, remember the ions are whatever appears to be the same on both sides. Well, that's not because polyatomic, so SO4. Well, here's SO4, and here's SO4. Okay, so I have something that's the same on both sides, so let's count them. Well, I have 1 SO4 here. I have 1 SO4 here, so that's good. Now I go to the nonmetals. Okay, when I look at the nonmetals, well, that's my Cl. So I have 2 Cls, and I have 2 Cls, so my Cl is balanced. And what do you know? My equation is balanced, and that's all it means to balance the equation. Now, quick reminder, what a chemical equation is showing you is simply the concise representation of the reaction. When we break it down, this is what we're looking at. If I have 1 carbon and 4 hydrogens and 4 oxygens, my yield sign, my equal, I better have 1 carbon, 4 oxygens, and 4 hydrogens, just like I had over here. It's balanced. Now, the reactants are always on the left. The products are always on the right. The nice thing about this that you want to notice is that our arrow here, our yields, always points to our products. So that's one way to look at it. And a couple of reminders, coefficients are always inserted to balance our equation, which we already know. I have to have 2 of these, okay, because of what's over here. So I had to have 4 total to have 4 total over here, 2, 3, 4, etc. So we always balance. Reminder, subscripts are simply the number of atoms in an element. Coefficients are the number of molecules in a reaction.